As I mentioned earlier, the gaps in these tentacle ridges might be a bit problematic. For my original simulation for this shot, I just collided with the tentacle ridges like this. But just to be extra safe, let's make some collider shapes for these tubes as well. And part of why I want to show this is just to show you another way that you can make some proxy collision objects. So for the body, we just did a basic shrink wrap. But for these tubes, we can't really do that because the shapes are far too complex. If we just isolate one of these tubes here, right now we don't have a decent attribute that we can use to isolate them. So instead of selecting by an attribute, I will select by 3D connectivity and grab one of these tentacles, hit delete. So this is blasting based on the primitive numbers, but it was able to select which of those are connected to each other in the actual mesh. I'll flip this to delete non-selected, and now because we have this fairly complex shape here, if we try to shrink wrap that, you can see how awful this collision approximation will be. So for more complicated meshes, we need to do something better. For the ground fracture, we used a convex decomposition, but for deforming geometry and deforming colliders, we often won't get very good results out of this. So for one, we'd have to turn the max concavity down a fair bit to get a good representation out of this tube here. And in this pose, that kind of works okay. But ultimately, we want to decompose this in the rest position. So let's take a look at what happens if we do a convex decompose on the tubes when they're in that rest pose. So I'll copy this split SOP for the tubes here, and I'll paste this over next to the main body proxy generation. Connect that to the rest position creature that we're bringing in. Let's actually move this creature scale to just after the object merge, so we can use that for these tubes as well. And let's grab this blast SOP and the convex decomposition once again. Let's see if this blast SOP works, if the primitive numbers are the same over here. And it looks like this blast SOP works fine over here as well because the prim numbers are the same. So if we display this convex decomposition, you can see we're not getting much detail in this decomposed tube here. We're actually getting less detail than in the original geometry that's fairly highly subdivided. And because this is a basic convex shape already, as we try to turn down the max concavity, we're not really getting any extra detail in this cylinder here. So convex decomposition doesn't necessarily work very well with objects at their rest position that are going to be then deformed into place. So I often prefer to use a Voronoi fracture for cases like this. So there are a variety of ways that we can create points for this Voronoi fracture. And actually a kind of interesting way to do it could be to base this on the lines that we're using to generate these tubes originally. So I'll drop in another object merge and point this to object context / creature / curves for anim. And as with the creature mesh itself, we need to bring this down to the creature scale as well. That's scaling it down by 0.7 so that these curves will match the actual creature's rest position also. And these curves have some points on them already. So if we display the points for these curves, you can see we're getting a fair amount of resolution on these lines already. And we can use all of these points on these lines to do our Voronoi fracture. We don't really need the primitive data on the lines, so you can just type in add, drop in an add SOP, and turn on this delete geometry but keep the points option. So that throws out the actual lines themselves and just keeps the points on there. And let's get rid of this blast SOP that's isolating one tube, drop in a Voronoi fracture, connect the split tube's first output to the first input of the Voronoi fracture, the points from our lines to the second input, and for the piece prefix, I'll call this collide tentacles tubes. So now let's check out our Voronoi fracture results, and let's do an exploded view. Okay, now you can see how the tubes are fractured up by all of the points that we passed in from those original lines. It doesn't really look much different visually from how it looked before. If we look very close in here, we may be able to see some slight difference in the mesh from what we saw before. Yeah, you can see there are some more cuts being created on the tubes after that Voronoi fracture. And this exploded view certainly helps us to see what all of the individual pieces look like. And now that we have these tubes cut up into all of these little segments, these little segments, once we deform them to match the tube animation, will make for some decent little convex shapes that we can collide with nicely in our RBD sim. And at this point, we've been using all of the lines from the original curves to do the Voronoi fracture. But if you want, you could just resample these lines for a different resolution. So let's drop in a resample here. Maybe change the length to 3. Let's go even further for the sake of demonstration. I'll turn that up to 6. So we have far fewer points now. You can see what that looks like here. And if we do a Voronoi fracture based on that, now we have much larger chunks. And I don't think these tubes at this resolution will do a very good job at representing the tube animation, because if we treat these as convex colliders, once these tubes start deforming, the convex shapes that are created for all of them are not going to represent the animation very well. Let's take a look at what that looks like. Now we've already set aside the tubes from the original animation over here. So I'm just going to create a null there so that we can easily reference this for our deformation. I'll call this animation tubes. And then over here, we're going to once again do a cloth capture and cloth deform. We can set aside our exploded view, drop in that cloth capture, connect the Voronoi fracture results to that, and we can capture it with the rest position of these tubes here. So they won't look much visually different from each other. These are the rest tubes, the Voronoi fractured version, and the cloth capture. And as we've seen before, we may need to reduce the radius of this cloth capture here. It looks like the tube's area of influence are kind of overlapping with each other. So let's try turning that down. Looks like a value around 0.5 should keep the different tubes from interfering with each other and affecting each other too much. So this will hopefully give us a decent deformation. And now let's drop in that cloth deform, connect the cloth capture to that, connect the original tubes to the rest cloth, and then for the third input on our cloth deformer here, instead of stretching a wire across our network and making the network view confusing, I'm just going to object merge in that reference to the animation tubes. So connect that object merge to the third input and point this to ... /animation tubes. And let's look at our results. And the display on this doesn't look quite right, probably just because the normals are wrong on this geometry now. If we set some new normals after the cloth deform, that should fix it. Yeah, this looks much better now, and we can verify that we're doing a good job of our deformation by comparing the results after the cloth deform to the animation tubes, and they're almost identical to each other. You almost can't tell that this one is the Voronoi fractured version. So let's bring back our exploded view just to reinforce the difference there. And I'll set this to just a very small amount of scaling in our exploded view here. You can see that this matches pretty well to the original animation. And this looks pretty good, but when we tell Bullet to treat a collider as a convex object, if the geometry isn't already convex, then it's going to do its own convex hull creation on the fly. And when we set up the Bullet solver, I'll show you how to double check the collision shapes that Bullet is creating for your geometry but just to give you a better idea at this point, let's set up a for each loop to create a shrink wrap for each one of these individual fractured pieces. So I'm creating a for each named primitive, connect our normal after the cloth deform to that input. So this will operate on each piece at a time. And let's do a shrink wrap for each individual piece here and display that output. And now let's display our original geometry after the cloth deform and compare that to the shrink wrapped version after the loop. And you can see that this shrink wrapped version, where it's doing a shrink wrap on each Voronoi segment, is doing an okay job. This might be enough collision accuracy for our particular sim here, but there is certainly some inaccuracy here. You can see wherever there's a fair amount of bend in the tube, the collider shape doesn't do a great job at representing that. So that's why we want to go a bit higher res with our Voronoi fracture here, so we can leave this view set just as it is. And if I bypass this resample on those lines that we're using to do that fracture, then now you can see that the shrink wrap of all those individual segments looks almost identical to the actual shapes of the animation. It looks like one nice continuous tube mesh. This is a very accurate collider, kind of to the point that you can't even tell that it's a bunch of separate pieces that make this up. You almost wouldn't believe me until I drop my exploded view onto these to show you that it's made up of all these individual convex hull segments. So this looks like a very convincing collider. Of course, there are limits to how far you want to push this accuracy. Right now we're creating almost 1,000 pieces to represent these tentacles here. So that's going to be another almost 1,000 deforming pieces that we're using for collisions in the sim, just for these extra tentacle tubes. And I don't think that will be terribly slow, but you do want to kind of be careful about just how much resolution you're pushing into these deforming colliders, because at some point you're going to start making things a bit heavy. So I'm going to leave this shrink wrap in here just so that you can see how to check what those convex hull accuracies will look like. I'll call this convex hull approximation check. And I'm going to leave it at this resolution unless we find out that our simulation is running too slowly like this. So everything looks all good here. We have our name attribute on primitives from our Voronoi fracture. We can make our geometry a bit more lightweight by turning off some of the groups and such. So on this Voronoi fracture here, for these colliders, we really don't need the inside or the outside groups. And we don't really need this attribute or group data on our tube geometry either, so we can do a bit of cleanup before the Voronoi fracturing and deforming of this. I'll drop in a group delete, put in a star to get rid of all groups there. I'll add an attribute delete as well. We don't need the path or the tentacle. And these might be only very marginal optimizations or speed ups, but as you've seen me mention many times so far, I just try to keep things as clean as possible. So now we have super clean tube geometry from our rest position creature with nothing but position and normals. We're not adding extra groups or attributes from the Voronoi fracture, except for this always important name attribute here. And then everything else on our setup for the tube colliders should be all good. Although I suppose after the cloth deform, we could also delete the cloth captured data. I don't really think it matters that much, but if you want to be obsessively clean about things, you can feel free to clean up stuff like that as well. So now these colliders are all finished. Let's once again do an assemble on these. Turn off the name attribute creation, turn on create packed geometry, and let's make sure it's picking up the correct name attributes, and this looks all good. Everything is named Collide Tentacle Tubes, except for the fact that I misspelled collide, which I will fix because that will drive me crazy. And with these final packed tube collider segments, we can just use the same RBD configure that we're using for the main body of the creature. So I'll just drag this down here. They just need the same attributes set on them because they're both standard deforming collider objects. So we can just merge those together and then pass that merge into our RBD configure for those deforming pieces. And check out the merge with the tentacle ridges as well. And of course, as usual, to keep things clean, I'll just drop in a null here, and I'll call this collider creature. So now we're all finished with our creature collision setup. And I know this seems like a lot of work just for a collider, but it's actually pretty normal for a lot of your rigid body simulation work to really be focused on creating decent collision objects. It's really a large part of the process. And actually, there's still one very important step that we haven't done yet. We've built these collision objects for the creature and its normal animation space, but if you remember from when we were doing our fracture setup, we're actually working in a smaller simulation scale. So I'm going to pin my viewport to this destruction area here, and I'm going to jump back to the fracturing setup just so that I can grab the same sim scale transform. So the sim scale that our fracture is set up at is 0.3, so let's just copy that. Go back to our collider setup here, and I'll paste in that sim scale after everything is all merged together, just before our collider creature null. So now we're finally all done with this collision shape for the creature. It's up to you if you want to include those extra tubes that we've made, or if you want to leave them out and see if the ridges are enough before including those. And it could also be worth checking how fast this is to evaluate frame to frame. So as I step through frames here, this is actually fairly slow to update just that one frame. So you may want to cache out these deforming collision shapes. And I suppose we could cache out the non-deforming packed tentacle ridges as well. That's kind of up to you. But this was taking me about 20 seconds, I think, for this to evaluate all of that. And I don't really want to add 20 seconds per substep to my simulation time. So I'm going to drop in a file cache. And I'm going to cache out each of these things separately. You could cache them all out together. That's up to you. But I'd like the flexibility of being able to turn off those extra tube colliders that we set up without needing to recache everything. So I'll call this cache body collider. Point this to job, geo, destruction. Make a collide body directory. Call this collidebody.vo1.$f3.bgeo. It's up to you if you want to use bgeo or bgeo.sc. Turn on load from disk and cache that out. So I was finding this incredibly slow to cache out that simple body collider mesh, so I stopped the cache pretty promptly, and I've opened up my performance monitor to see what's happening here. And just judging by the readouts in the bottom left-hand corner of Houdini showing what it was cooking, it looked like the assemble was going quite slow. So instead of doing an assemble, I've also dropped in a simple pack sop, which will just create packed geometry without doing some of the other things that the assemble sop does. And when we pack based on this name attribute, this name attribute becomes a primitive attribute, but ultimately we want those name attributes to be on points, like what we get out of the assemble. So when you do a normal pack, you have to do a promote to push that name attribute from prims down to points for your simulation. So I set up both the assemble and this pack and merged those together, and I opened up my performance monitor and told it to start monitoring that. You can find the performance monitor under the Windows menu or hit Alt-Y. And then evaluating a new frame showed that yes, the assemble was in fact most of the slowness that we're getting on each frame's evaluation. Each frame was taking 22 seconds here, and 13 seconds of that is just the assemble SOP alone. So if we get rid of the assemble and just do the pack and attribute promote on the name, that's taking almost no time at all. If you look down on the performance monitor here, you can see that this pack1 node is taking essentially 0 time. Same thing with the attribute promote. So whenever things are running more slowly than you'd like, it can be quite helpful to do this analysis, and it does show you this sort of heat map display in your network view here so that you can really visually see which nodes are the problematic ones. In addition to this assemble, which is the main slow node that we're dealing with, this normal node is also quite slow. So we can potentially just get rid of that. That was just meant to help the geometry to display more nicely in the viewport. But because we're just dealing with collision geometry, we don't have to care that much about it displaying perfectly in the viewport. So we can either get rid of that normal node or just try putting it on the geometry before the capture or just after the capture but before the deform, because you can see that anything before the cloth deform here doesn't have to happen on every frame. If something is slightly slow before the cloth deform, it doesn't matter that much because it only happens once. Because the cloth deform has that animated input and output, you can see that represented by the little clock icon here. Anything from there on that's running slowly is going to be more problematic because it's evaluating every single frame. So we can stop our performance monitor, and to get rid of this heat map display, I'll just hit record again and stop again. That will get rid of that colorization and the network view. So let's delete this merge that's combining the assembled results and the packed results. Let's delete the assemble SOP. And let's move this normal to just before the cloth capture. And then we'll wire in this pack and attribute promote on that name attribute to just after the cloth deformer. And now if we display this attribute promote here, and then hit Alt-Y to bring up our performance monitor, let's hit record, and then step ahead one frame and see how long this takes to evaluate now. So this is still not super fast. It took a little bit more than 10 seconds, but by moving that normal SOP and doing the pack and attribute promote instead of the assemble, we've cut our evaluation time per frame to less than half of what it was a moment ago. So that's going to help us out quite a bit with our caching, and it'll especially help you out if you're running something like this live in your scene without this intermediate cache. Now, another very important thing to do here is to delete the cloth capture attribute. The cloth capture and deform added thousands of these cloth capture attributes, which is making the geometry very heavy, and I encountered problems with this that you'll see in a later video that I will clean up and discuss a bit more then, but I would recommend at this point to delete this attribute now and save yourself some trouble. Now, because that is such a speed increase, I'm going to copy this pack and attribute promote. Let's go over to where we're assembling the tube proxies as well. Let's delete that assemble and paste in our pack and attribute promote there as well. Wire that in on our tube proxies also. And similar to before, let's just make sure that we're not doing the normal evaluation on every frame. So it doesn't look quite as nice in the viewport, but that's not really a big deal. These changes are worth it for the speed increase. Then I'll copy our body collider cache, paste that for our tube proxies as well, rename that to tube collider. We'll also make a separate directory for this called collide tubes, and name this collidetubes.vo1.$f3.bgo. And now both these tubes and this main body collider mesh here should both cache a whole lot faster. So we'll go ahead and save both of those to disk. And now after caching both the body collider and the deforming tubes collider and merging those with those packed tentacle ridges and ends, everything is responding much more quickly in the viewport here. Now, as I've mentioned a few times over, I don't really know if these tube colliders are necessary. When I did the first version of these destruction shots, I didn't bother including them. I just collided with these ridges here. And especially as we're doing our initial setup of this RBD simulation, I want to keep things as lightweight as possible. So I'm just going to disconnect this tube collider here. And then once the RBD sim is working, if it looks like there's some weird collision stuff with pieces passing through these gaps between those ridges there, then I'll go ahead and reconnect those tube colliders. But for now, I think this is looking pretty good, and we can move on to creating a collision mesh for the ground that's around the area of interest, and then finally start running our RBD sims.